Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning, everyone. So, can you guys hear me? There's a sound check.
Yes, doctor.
Okay, all right, good. Okay, so today we are already at week 3, and this is a new topic on week 3. So let's see. So this is our planning. So this is first week. So already covered signal, discrete time signal, and last week discrete time system. So today we are going to look at a very special system. Okay. Last week we have seen generally what is a discrete time system, but this week we will start looking at a very specific, a very special discrete time system. And the rest of the course, until week 14, so we are going to focusing on the LTI system alone. Okay, we're not going to look at the nonlinear system anymore. Okay, so we will stop at week 2 on that one. The rest will be on the LTI system because this is a very special system. So we're going to look at it today. Okay, and okay, so this is so that's why the title is a LTI system. Hopefully, we can finish this module today, the 2 hours. So we have 2 parts. So the first hour is first part. So we're going to look at on the introduction on it, and then the second part is more on how the process within the LTI system. Okay, so what is the LTI system? LTI system is what we call that L. That L is actually linear. Okay, and TI is a time invariant. Okay, so that's the T and I, time invariant. So LTI system is actually a linear and time invariant system. Okay, a very special system, and we are actually using this a lot in our system, in many of the digital discrete system. Okay, and LTI system is not new to you guys actually, because you have there's a one control cost. There's a signal X system, especially cost, and even actually from your circuit theory, you already look into this LTI system, whether you realize it or not. So actually you already seen this since circuit theory, the linear and time invariant system. Okay, and those courses, a lot of courses, 3 to 4 courses, actually covering a linear and time invariant system. Those courses are actually covering a continuous system, continuous time system. So what is the difference on this course? So we will look into this LTI system again, but in a discrete version. Okay, where fortunately everything becomes simpler and easier. All right. Okay, so the system is linear and time invariant because last week, if we can recall, we have looked into 4 properties of a discrete time system. So one is the linearity, and then time invariant. We are checking it, either it is a time invariant or time varying, and then stability. The last one is a causality. Okay, four properties. But this system, this is a special system. So what has been fixed is it is linear and time invariant. So the stability and causality, we need to check that one later, right? So the one which is fixed is linearity and time invariant. So we need to make sure that the system is linear and time invariant. So recall from the previous chapter, a linear system, right? So actually this is some a summary from last week. So a linear system is a system where there is a no operation such as power. So you shouldn't have a power operation, a log, a cosine, and sine. Okay, so these are it's like if you see this kind of operation, so actually automatically we know that it is not linear. It is not linear. So we need to avoid this operation. So if it doesn't have this operation, then it is actually linear system. For time invariant, variable n, what is a variable n? Variable n is the time, discrete time. Okay, so again, hopefully everybody already familiarized with this variable n. Because previously when you do a continuous time system, So that n is actually t in second. The unit is a second. Time with unit second. Now, everything is discrete. Time is replaced with n. So what is n? N is index. What is the units of index? There is no unit. It's just a sample 0, sample 1, sample 2, sample 3, sample 4, those kind of thing. Okay, there's no units. But we can translate that n into t. So there is a formula for it, if you still remember. So what is t? T is actually, what is the conversion formula? T is equals to n ts. Okay, that n. So we can change that n into t by knowing the sampling time. If you know what is the sampling time is 1 over frequency sampling, right? So that's a logic, because this is from t to n. So we have what we call a sampling process. A sampling process needs sampling frequency. Okay, 1 over fs, sampling frequency, it is what we call a sampling time. So this is the relationship. All right, so in time invariant system, variable n must not be accompanied with any mathematical operation except plus and minus. Okay, so within the time bracket, so let's say we have, for example, we have a yn equals to xn plus, let's say this is a 2x and let's say a 2n. So automatically we know that this one is fine, because there is no because what is the rules here? Variable n must not be accompanied with any mathematical operation except plus and minus. Actually, this is nothing. So we do nothing to the n. So this is what we call a current time, which is an n. But this one, so we have multiplication to the n. So we need to look into whatever inside the time bracket. Okay, because this is about time. So we are looking at the time bracket. So this is multiplication. Multiplication is not allowed, right? So the one which is allowed is just plus and minus. Automatically, we know that this is not time event. Okay. And the linearity, because this is just xn, there's no operation to xn. So unless you have, let's say, a square, so this square makes the system becomes non-linear. Okay.
Hello, hello, hello. Oh, okay.
Okay, I'm back. Sorry for the interruption. Let's see. So someone is writing on the chat. Xn square is still time invariant, right? Yes. If it is just xn square, it is still time invariant. So, but not linear. So that one is true. Okay. So that's actually an easy check on how if we look into this system, whether it is linear or not linear, time invariant or not time invariant. Example of let's say one system which is LTI system, which is a linear and time invariant. So this is one of the example. Let's say this is a xn plus 2xn minus 1 plus xn minus 2. Okay, so we can see that. So there is no power, there's no log, there's no cosine, there's no sine operation to the signal value. Okay, to the signal value. And there is no, what we have on the time bracket is just minus. So this is minus. So there's nothing here, nothing here. So this is where you have only minus, which is minus 1. And then this is minus 2. Okay, and it's still fine if, let's say, this is plus. All right. And this is a multiplication to the signal value, which is allowed. Okay, so this is the only things which is allowed, which is a multiplication, and then summation. So this is one signal value, which is at current time. This is a signal value delayed by 1, right? And this signal value is multiplied by 2. And this 3 signal value is actually sum. Okay, so we take total value of this 3 signal value. So multiplication and sum is allowed. Power, sine, log, those things are not allowed. So this is the only operation which is allowed to the signal value: multiplication and sum. And for the index, for the time, which is the inside the time bracket, so the one which is allowed is just either minus or plus. Other than that, if you have that, then it is not time invariant. So what we have is actually now, if it is a LTI system, such this one, so we are actually having a very simple equation, very simple equations, because we just have a few operation. One is a delay, so this is either delay, a minus or plus, and then just a multiplication and sum. That's all. Only 3 operation. Only 3 operation that you will have in an LTI system. So that's why everything becomes quite simple. Okay, and LTI system representation. So this system, this kind of a system, this one, this LTI system. So actually, we can represent it. We can represent it. Representation means that if we are, if we say, I have a system. So how do you show the system? Okay, so you can represent the system by 2 things. One is a difference equation. So this is actually difference equation because we call it equation. So it represent LTI system in terms of its input and output signal. So actually this is difference equation. Okay. So equation which is relating input and output, because if you recall, what is a system? A system is where you have inputs. So this is the input. You have output. You have the process. You have the process. And this system will actually convert or change the input signal into a new form of signal, which is Yn. Okay, and simply, this equation is called difference equation. So that's how one way of representing our LTI system. Okay, so this is the one that you have seen so far, the LTI system, the equation. So we call it difference equation. For continuous time system, previously in your previous courses that you have learned, so that difference equation is called differential. We call it differential equation. Okay, discrete, we call it difference equation because of the time operation. Because of the time operation here, we have n minus 1, n plus 1, because actually this is n minus 2. Okay, so we still call it a delay. So it's a difference. So a difference of time. Previously, if it is a continuous time, so actually we cannot do a difference of time because when it is a continuous, we need to do a differential. So you need to do that d over dt. So that d over dt is actually differential operation. Okay, actually differential of time is actually difference of time. So it's just a naming of either it is a continuous or discrete. One is we call it differential for continuous. Discrete, we call it difference. Okay, so the other one to represent this LTI system, which is, this is what we call an impulse response. Okay, represent LTI system based on the system transfer function. And impulse response, this is very unique. So we can have a unique or a single impulse response only for LTI system. If the system is not linear, if the system is not time invariant, you cannot have a single impulse response. You might have an impulse response, but maybe not one impulse response. You might have more than one impulse response. Okay, so that's why LTI system is good. Because even the impulse response, you will have only one impulse response, and then so that's why we can use this impulse response to represent our system. And I already give you one video on what is the impulse response in e-learning. So what is the impulse response? So can anyone respond? Impulse response, respond. Let's see your response. So can anyone explain a bit what is actually what is this impulse response? Because anyone?
I will try.
Yes, please.
The impulse transform is the fundamental response that cannot be broken down any further.
Yes, that's exactly which the video explained.
Yeah.
Okay, so we will see that. So what does that mean? So it is like a component. Okay, impulse response is like a component which is a component of the system, which cannot be breaks into a smaller part. Okay, it's like the smallest part of a system. So when you combine a few of these things, so it will represent your system. Any other answer? Maybe some simpler explanation from that one, or in any perspective, other perspective. Anyone want to try? You can also write it on the chat section. So let's see your understanding, because actually this is not the first time you heard about what is the impulse response.
Impulse response.
Please try at least one more answer. At least one more response from you. So we need to use that word. So what is actually response generally?
Doctor. Reactions.
Reaction of
The system in response to some external change.
Okay. So a close. So a feedback. Nabil write it as a feedback. Okay. So yeah, almost. You guys have some important keywords there, right? Like a feedback, so response. So actually, a response is output. Okay, response is actually output. So, and impulse. What is impulse? Impulse is a signal. So we have seen this in our first week. So we have two types of basic signal, right? So one of it is an impulse signal. Another one is a step signal. So actually, if you can recall, there's a course, one subject, I think a control subject. So that subject actually already introduced you to two types of response. One is the impulse response, another one is a step response. Okay, you do something, put a step signal, and then see how your system will be stable after a certain period, right? We can still remember that. So you do that with step signal. That plot is actually step response. Okay, so what is a impulse response? Impulse is just an impulse signal. Impulse signal. So we have defined impulse, which is a delta n at index 0. So the value is 1. Okay, so this is definition of impulse signal in discrete time, for discrete time signal. Okay, continuous time signal, the definition is a bit different because everything's supposed to be continuous. The x-axis is continuous. So it's not on a single point. This one is on a single point, which is 0. Okay, I'm not going to explain that continuous time impulse in detail. So what we have is actually you have this signal, and then you have a system. So you're going to fit this impulse and then get something. So this one is actually response, output, feedback, response. Those are the same thing. Okay, those are the same thing. So if you have a system here, so this is our system. Our system. What is a system? System is something that's change the input signal into a new form of signal, right? That is the operation here. So we have some operation. And operation which is allowed for LTI system. So what is it? So it's just multiply to signal value. So that is 1. And then we have a summation. And then another one is a delay. Okay, on that index, delay. So that's our system. So if then we can say that we can have a lot of a combination of multiplication, summation, and delay, because those will describe our system. So you have input. So this is the input. So you set your input as an impulse. This one, feed it into the system. Feed it into the system. You will get something at the output. Okay, let's say the output is 2 to 1. Okay, if your input is an impulse, you feed it into your LTI system. At the output, you get this one. Okay, so actually this is your impulse response, because response is the output, right? So this is what we call impulse response. Output is a response, input is the impulse, then we call it impulse response. Okay, so and this is very important because this one will describe our system. This one will describe our system. And actually, what is the impulse? Impulse is the smallest entity of a signal that we can have. So that's why we call it, you cannot break it into another smaller signal. So that's the smallest signals that we have, because we have only one sample. So if you have a 0 sample, means that there is no signal at all. Now you have one sample, the smallest sample that you can have. Okay, you cannot have a half sample because this is a discrete, so it's a 1 sample, and the value is a unit value, which is 1. Okay, So when you run that, so actually when you give this impulse response, because this is actually when you give a very the simplest form of a signal into a system, so actually the output will describe the system. The output will describe the system. So actually this system is actually can be represented by 2, 2, 1, by a signal, by another signal. This system is represented by this signal, which is a 2, 2, 1. And this impulse response, the notation is we put it as a H. And okay, that impulse response. So this is where. Okay, I'm going to write it here. Now, generally, we are writing it as the Hn. What is the impulse response? Impulse response is actually we use it as to represent the LTI system. So this center box is our system. So this is the one will change. This is the one that will change Xn, the input signal, into a new form of signal at the output. Okay, for example, Xn is a very noisy signal, Right, it's a lot of noise, and then we process that. We're going to filter that noise. So Hn will filter that noise. So output will be a clean signal. So who clean it? Hn. So Hn will clean that signal. Okay, so that's why this is very important, because we can do a lot of manipulation using Hn in implementing our system. Okay, so this is very important. So what do we have here? Either we are representing the LTI system using a difference equation, the equation that's the normal equation that you see. So yn equals to something, something, something. So you have a xn and yn. That one is called difference equation. And then what is the impulse response? This is very unique to LTI system, because we're going to have a unique impulse response for LTI system. So we can use it. If it is not linear, if it's not a time invariant, so it is possible to have impulse response, but maybe not a single impulse response. Maybe you're going to have a lot of, or maybe infinity number of impulse response. Okay, so that's why LTI system is very unique. So because of that, we can represent the LTI system using impulse response. So which is so this is the story. So this is how we get the impulse response, because we get that signal from impulse. Okay, then we write it that way. So let's see if I have that diagram. All right, so whenever you see this diagram, xn and then yn at the output, and that box written as Hn, automatically this is LTI system. Okay, so if it is not LTI system, we cannot put it this way. We cannot use this. So when you have Hn as the impulse response at the center, which is representing the system, so this is actually LTI system. Okay, let's get back. Okay, any questions so far? Because this is quite conceptual of what is actually impulse response. Okay, and this is actually a general equation for the difference equation. Okay. Okay, so what is it again? So this is actually a difference equation, and this is actually a general equation for it. Okay, let's see. So how do we get into this equation? Because this is very important, because we need to understand, because when LTI system, we have two things. One is a difference equation. Another one is that impulse response. So we need to understand what is this equation, because this is the difference equation. So okay, let's get back to our a simple example just now. So we have xn plus 2xn minus 1 plus, so this is actually xn minus 2. Okay, so if we want to simplify this or make it into this equation, so this is actually, so that's why we have this summation. Okay, this summation. And by index, so this is where we can put it into a summation. You can see two things here. One is x, another one is y. So let's do this one first. So this is a summation from, let's say, index of n, starting from 0 up to 2. And then we can say that this is a b n. Is it bk? Okay. Sorry, this is k, bk, x, n minus k. And that bk is actually equals to the first one, which is at index 0, because this is a k equals to 0, b0, which is a k0, that one is a 1. And then when index 1, it is 2. And the other one is 1. Okay, so that's how we convert that equation, this equation into this general equation. So summation, because we have a range from 0, when this is a 0, so this is n minus 0, you get n. When k is equals to 1, this is n minus 1. Right, up to 2, because this is n minus 2. And what is the bk? Bk is 1, 2, and 1, the weight. So this is what we call weight. Right, so what is the weight for the first signal value? 1. What is the weight for the second signal value? 2. And this is 1. Okay, so this is why we can, and if we look at here, so it's not only we are considering input sequence here, so we can also have several other output sequence. Because in this case, we have only one output signal. Okay, one output signal value. So we can also have a yn, let's say plus 2yn minus 1, and plus, let's say 4yn minus 3. Okay, so we have, this is no delay at all. So this is delayed by 1, this is delayed by 3. And then equals to xn. Plus, let's say the same thing on that one. So this is where we have both sequence on input and output. It's not only input that we have several sequence, but output also has several sequence involved in this equation, in this difference equation. So this is where we can summarize it into this kind of thing. If the weight multiplied to the input is, we call it bk, the weight multiplied to the output, we call it ak. Okay, one is the b, another one is a. Okay, so let's read this one. So when the LTI system consists of output sequence, the system is said to have a feedback. Okay, so this is a feedback system. In the LTI system, the weight of the input and output sequence will determine the transfer function of the system. That means the Hn. So what is the transfer function? That Hn, the impulse response. The name difference equation comes from its continuous version, which is called differential equation. I think I already mentioned this, where differential operation is used to obtain the differential equation from the Laplace transform. Again, this is from last courses. So you have seen a Laplace transform in several courses previously. For discrete system, Laplace transform is replaced with Z transform. This is later. This is we're going to look into Z transform next week. Okay, So, but the one that you have seen before is actually Laplace transform. So, but this is the important point here. The weights of the input and output sequence will determine the transfer function of the system, which is the Hn. Okay, so means that, so we should know how to, let's say this is your dE into Hn. So we need to know how to convert difference equation into Hn, and we need to know how to convert impulse response into difference equation. Okay, we should be able to do that. So we're going to look at maybe one or two example on that one. I'm going to skip this example. This is actually on how to prove the impulse response, some theory on impulse response. So I'm going to skip that one also. You have seen this. Okay, let's see. Example number 2. Find the impulse response of the difference equation below. See, because we need to know how to convert difference equation into impulse response, and from impulse response to difference equation. And this is our difference equation, because clearly, so we have yn equals to, there's a xn, there's a yn, there are some operation. Okay, and you need to make sure that the operation is only a delay, weight multiplication, and sum. And this is actually sum to a minus value. Okay, so if you have other than that, so means that this is not difference equation, it's not LTI system. And this is confirmed, this is LTI system, because we have no other than summation, multiplication, weight multiplication, and delay. So we have only those 3 operations, right? So this is the LTI system. So impulse response is the weight of the input sequence. So thus, Hn is equals to 1. So this is actually 1, the weight is 1. This is, the second one is 2. And the n minus 2 is not there. So that's why this is a 0. So this is index 0, index 1, index 2, index 3. This is index 0 because there is no delay. Okay, this is index at index 1 because we have a delay of 1. Okay, no index 2. Index 2 is a 0 because there is no signal value. So actually this is plus 0 plus 0 of x and minus 2. Okay, just because of that 0, so that we put 0 here. And then minus 3. So in this example, it is very straightforward. The impulse response is just by taking the weight, So whatever the weight is, so you just take that one. So we can put it as a Hn equals to 1 to 0 minus 3. Solve. Okay, very simple. And there is a note here. Definition of impulse response as the weight of input sequence is only true if there is no past and future outputs. So there's no output sequence. So because we have only a single yn. So but if we have this thing, so let's see where is. This one, this example. So you have several other output sequence. So there's a yn minus 1, there's a yn minus 3. So we cannot do that. We cannot use that formula. We cannot just take input sequence, the input sequence weight as the Hn. We cannot do that. Okay, this is only, we can do this if there's only an input sequence only. There's no other output sequence. Okay, we will look at a broader definition of the impulse response in future topics. Okay, so at this moment, at this week, so we will cover only how to convert from a difference equation into impulse response, and impulse response into a difference equation if we only have input sequence only. What is past and future output here, doctor? Past and future output is, again, hopefully I already answered that, but I'm going to repeat it. Last week, we have learned something about causality. And causality, there is what we call future input, past input, current input, and it also applicable to output, current output, future outputs, and past outputs. Okay, so whenever you have n without any delay, so that what we call current time. So this is current input, we call it current input. This is current outputs. And if we have a delay, -1, so this is what we call a pass input. This is also pass input. This is pass output. This is pass output. Okay, but if you have yn plus 1, whenever you have plus, so this is actually future. So this is future output. Whenever you have, let's say, 3xn, for example, plus 2, so this is future input. Okay, so you have future input, you can have a future outputs. So that's related to actually causality. What is a causal? A causal system, you cannot have a future input or outputs. Either input or outputs, you cannot have those future values. So what is the last one? Okay, let's do one more example. Let's say because this is from a difference equation to impulse response. So let's do one example from impulse response. Let's say we have an impulse response of Hn equals to 2, negative 3, let's say, and then 5, 0.1. Okay, so let's say this is our Hn. So what is this? So this is impulse response. So what we want to do here, convert it into a difference equation. So why we are doing this? Because we already know that LTI system can be represented by either impulse response or difference equation. So we need to know how does LTI system looks like. So when maybe someone give us, okay, I have a system, LTI system, and this is my impulse response. So this is the impulse response of the system. So then later you want to implement it. You want to implement it, okay? Either on a microprocessor or maybe some VLSI architecture, those kind of things, some hardware, or maybe just doing some programming. Okay, so in that case, so you might want to convert this into a difference equation, because when you want to have an output, so you should have your difference equation. Okay, so then it is very simple. So because we already know that what is this value? This value is actually the weights for the input sequence. And we know that this is on index 0, index 1, index 2, index 3. Okay, then the difference equation will be 2xn minus 3xn minus 1 plus 5xn minus 2 plus 0.1 xn minus 3. Okay, very simple. So this is a very simple conversion. Okay, another question, if it's only yn, is it still considered an impulse response? So we cannot have one equation which is yn. I think the question is, okay, for example, we have yn equals to something. Okay, we cannot have one equation which is a single yn. There's nothing here. So hopefully I'm answering the question. Okay, and then because actually I'm not really understand what does that mean. If it's only yn, is it still considered an impulse response? So can Umar, can you explain a bit? What do you mean by that?
Now I was referring it to as the current
Only current output. There's no.
I realized that that is sitting on the left hand side of the equation.
Yes, no problem. We can have that one. Okay, we can only have a yn. So it is still a difference equation. Whenever you see this equation, either you have only current outputs or you have another other sequence of outputs. So it is still considered a difference equation. It is still considered a LTI system.
That is, sorry.
Yeah, continue.
It's not considered impulse response when there's yn plus minus anything lah.
Okay, impulse response is different. You need to convert. You need to convert this difference equation. So this is difference equation. So it is in a different form. What is the difference equation? You will see an equation which you have this equals, and then there is a xn something sequence, and then yn. You can have also yn minus 1 or yn plus 2, those kind of things. You can still have those things. And this is called difference equation. This is not yet impulse response. Okay. So this is why to represent a LTI system, either using a difference equation, you have another option, which is represent it using impulse response, which is this one. Okay, and in this example, so we don't have the output sequence yet. So we will see that later. We will see that later. Okay, example on we have on converting a difference equation with output sequence other than yn. So we will see that example later. Not this week. Not this week. But yes, we can still convert it into hn. Okay, so we can do that. At the moment, we do the easier things first. Okay, the easier part first. So which is we doesn't have any other outputs, other past or future outputs. So we only have current outputs. So if we have only current output, so this is how you convert it. You just take the weights multiply to the signal value of the input signal value. Right? Very simple. Very simple.
Okay.
Okay, before we stop for the first session, so I just want to, so this is types of impulse response, because we already know what is the impulse response. Impulse response, if we look here, so what is the difference here? So impulse response is actually, it looks like a signal, right? This is just a sequence of value. So what is a sequence of value? A sequence of value is actually, if we go to the first week, so that one is actually a discrete time signal. Okay, with index, those kind of thing. So, and when we are looking into a discrete time signal, so we are, one of the thing is we are actually, we can count the length. So what is the length of this one? So the length is a 1, 2, 3, 4, because you have 4 samples. So the length is a number of samples. And previously, we can also say that we know that so one signal, the step signal, so it starts from 0 and then 1 and then 2 until infinity. Everything is 1. So this is a step signal. So how many samples that we have? So we have infinity number of samples. Okay, so we have learned this. So if this signal is impulse response, if the signal is an impulse response, so this is where we can categorize it. So the impulse response, the length is finite, so we call it finite impulse response. Okay, very simple. If the impulse response has an infinite samples, so we call it infinite impulse response. So then now we have 2 types of impulse response. So this is new in continuous time system. So we doesn't have FIR. So actually everything is IIR. But of course we doesn't call it IIR because because you only have one, so it doesn't have to call it, you don't have, it doesn't have to name it because you have only one. But for a discrete time system, so we have two, because the impulse response can be finite. For example, the previous example, you have only 4 samples, finite. You can have infinite impulse response. For example, it is a step signal, okay, because the sample is infinity. So that's why IIR. So the finite infinite terms are referring to the size or length of the impulse response. And for FIR system, so difference equation for FIR system is where there is no output sequence. There's no output sequence. So you just have a single yn. So there's no yn minus 1, yn plus 2, no such thing. Okay, that one, we call it FIR system. So we have only this xn, the input sequence. So means that this example, this is FIR. So this is FIR. Okay. And this one, the one that we have seen, because previously we doesn't know what is the name. When you have an output sequence other than yn, so this is IIR, infinite impulse response. Okay, but so far we do not know how to convert this equation into to the impulse response. We don't see that yet. Okay, we don't learn that yet. So what we have done is only if we have no output sequence, what we have is only the input sequence. So we already know how to convert from different equation into impulse response, which is very straightforward, just taking the weights, right? So if you have the output sequence, we don't do that yet. So that one is maybe in next week, not this week. So what you need to know now is this one. So we have FIR and IIR, so the times, okay? And generally FIR, we doesn't have the output sequence, so that's why the equation becomes, we can simplify the equation into this thing. So we have only X only here. There's no Y, there's no summation of the outputs. Okay, I think we stop here. We take a rest, we take a break for 10 minutes, and we'll come back at 12:10. Okay, using a new link. Okay, do not use this link. So there's another link in the, you can get it from e-learning. Okay, use that link. Use the week 3 class 2 link. Okay, so see you guys again in 10 minutes.